So far, we established that light is a wave and can be described with the mathematical equations that describes waves. However, we have two mysterious phenomena that were not possible to be explained with that description of light. First one is called the black body radiation. And it simply describes the fact that when you heat up anything to a high enough temperature, it's going to start glowing light with different frequency. That's the case for the sun, for example. It's just a very hot object that emits light with different frequencies. It emits what we call a continuous spectrum, a spectrum that contains all frequencies, all colors of light. If you look at that spectrum for a hot object like the sun, and you try to see how the intensity of the light correlates to the frequency of that light emitted, we'll see that experimentally, actually, the intensity increases with frequency and then it decreases back again. The first attempt to explain this was just assuming that light is simply a wave, so we can deal with it like a wave. And the intensity of a wave is simply given by this formula right here. So it's going to equal a constant times the square of the frequency. And that is the classical description for the intensity of a wave. So when we apply this to light, we will see that this clearly works for lower frequencies, but it clearly doesn't work for higher frequencies. It actually predicts that higher frequencies should have higher intensities, which is not the case. Otherwise, we should have been dead, because the intensity of higher frequencies that are lethal to us could have been higher than usual. The second attempt to explain this was done by Planck, and he actually got Nobel Prize for that by introducing a revolutionary concept at the time, which is light is quantized. He simply used a formula that correlates the intensity of light to the frequency that included the same classical term describing the wave, which worked perfectly for lower frequencies, but then he introduced a new term that he called the quantum term, shown in this expression right here. When he did this, his model was actually able to predict that above a certain limit, the intensity of light will start decreasing with frequency. That quantum term is basically based on that light as a form of energy is emitted or absorbed in discrete amounts, or whole amounts of energy that are called quanta, or in case of light is called photons. Beam of light is not a continuous beam of waves. It's actually discrete packets of waves that moves forward with the speed of light. And mathematically, that means that the energy of any photon is only proportional to the frequency. And based on this idea, we can explain the different regions of electromagnetic radiation, because the energies of different regions of electromagnetic radiation are going to be proportional to frequency. We see the scale of different frequencies of radiation. We see different regions depending on the magnitude of frequency or wavelengths, starting from long wavelengths in the radio wave region, and then shorter wavelengths in the infrared region, and then even shorter wavelengths as you go to the visible region, then the ultraviolet, then the X-ray and gamma ray. Energy and wavelengths are inversely proportional. So the shorter the wavelengths, the higher the energy associated with that light in that case. And that's opposite to the trend if you describe your radiation with frequency. So the higher the frequency, the higher the energy associated with the light in that case. And if we focus on the visible region of light, different colors will correspond to different wavelengths or different frequencies, and the energy associated with the color goes in this order right here, starting from the lower energy red light going to higher energy orange, then yellow, then green, blue, violet, and so on. The second skill that we should learn in this context is calculating energy associated with certain frequency or certain wavelengths of light. If we have two different photons with 5.00 times 10 to the power 3 nanometer, which should be in the infrared region, in comparison to a photon with a wavelength of 5.00 times 10 to negative 2 nanometers, which should be in the X-ray region. According to our previous discussion, the infrared region should have much lower energy than the X-ray region. And let's see how mathematics will back this. So the first step is going to be converting wavelengths from nanometer to meter using SI prefixes. So we take the 5.00 times 10 to the power 4 nanometer, multiply it times 10 to negative 9 meter, divide by 1 nanometer. Nanometer will cancel out with nanometer, and we will get the wavelengths in meters. Second step is going to be taking this value of the wavelengths in meters and substituting it into the Planck's formula. So energy is going to equal hc over lambda, so it's going to equal 6.6 3 times 10 to negative 34 joule second times 2.99 times 10 to the power 8 meter per second. And then we plug in the wavelengths in meters that we obtained from the first step and carry out the math, and we'll see that the units will cancel out and you will get an energy which should equal 3.97 times 10 to negative 21 joules in this case. We repeat the same thing for the second photon. So we're gonna just plug in the values for the Planck's constant and the speed of light, and plug in the value for the wavelengths after we convert it to meters by multiplying times 10 to negative 9 meter per 1 nanometer. You will get 3.97 times 10 to negative 14 joules. It's clear that our prediction turned out to be correct. The infrared photon has a much smaller energy in comparison to the X-ray photon. It's actually like 6-fold increase as you go from infrared to X-ray regions.